SwayamPrabha. Digital India. Educated India.
Lecture number 39. Slowly we are moving towards the end of this lecture series. This lecture is also dedicated to non-textile use of natural dyes, and here we will be discussing about the dye sensitized solar cells. Solar cells have been in fashion and use as an alternative renewable source of energy. Introduction to this new concept of dyes sensitized solar cells, let us try to take a look as to what is the role of dye in trapping the sunlight and how does it convert it to electricity. Now, it is a completely different use of natural dyes, where dyes in general were first used, synthetic dyes, and now we will also understand how natural dyes are used in this dye sensitized solar cells. What is a dye sensitized solar cell? A dye sensitized solar cell is a low cost solar cell belonging to the group of thin film solar cells. It is based on semiconductor formed between a photosensitized anode and an electrolyte, a photochemical system. So, it must have a thin film which is of solar cells, and it must be made up of semiconductor material which should have a photosensitized anode working as a photosensitized anode, and there should be an electrolyte to carry out photoelectrochemical reaction. Cost effective renewable energy. The quest for cleaner and cost effective renewable energy has led more research attention to the focus on dye sensitized solar cells, DSSCs, also known as Gratzel cells. The DSSCs have advantages: chemical versatility and facile synthetic approach to diverse molecular structure, energetic and structurally tunability, low cost and eco-friendly or environment friendliness. DSSC is made up of 5 components: a conducting mechanical support, a semiconductor film, a sensitizer, a redox couple which is an electrolyte, and a counter electrode. Fine tuning any 2 or 3 of these components have resulted in DSSC with increased efficiency. So, this dye sensitized solar cells or DSSC are now in vogue. First solar cell or Gratzel cell. The first version of dye solar cell was known as Gratzel cell, was invented by Michael Gratzel. So, it is more popularly known as Gratzel cell because that was the first model of trapping solar energy and converting into electrical energy. And then we will see where does the dye play a role. In a traditional solar cell, it is made from 2 doped crystal, one doped with N type of impurity, that is, it is an N type semiconductor which add additional free conduction band electrons, and the other doped with P type impurities, which is P type semiconductor, which add additional electron holes. So, basically you are trying to make more and more electrons conduct by using two different types of semiconductors. One is the N type semiconductor and the other one is the P type semiconductor. How does a solar cell work? When placed in contrast, some of the electrons in the N type portion flow into the P type to fill in the missing electrons, also known as electron holes. Eventually, enough electron will flow across the boundary to equalize the Fermi levels of the two materials. The result is a region at an interface of the p-n junction where charge carriers are depleted and or accumulated on each side of the interface in silicon. The transfer of electron produces a potential barrier of about 0.6 to 0.7 volt. So, you see, all that happens at the interface of these two materials, and because there are conducting electrons in one region and there are some holes of electrons, that means these electrons have been ejected out. So, those holes have been filled by conducting electrons. So, this is what the broad spectrum is the fundamental of solar cell, and this is how it works. So, we have to focus more on where the dye will play a role. Slowly we will move to that. How does it trap solar energy? When placed in sun, photons of sunlight can excite electrons on p-type side of semiconductor, a process known as photoexcitation. So, these electron holes were generated by the incident of sunlight, and this process in the p-type of semiconductor is called photoexcitation. In silicon, sunlight can provide enough energy to push an electron out of the lower energy valence band into a higher energy conduction band. As the name implies, electron in the conduction band are free to move above the silicon. When a load is placed across the cell as the whole, these electrons will flow out of the p-type side into the n-type side, lose energy while moving through the external circuit, and then flow back into the p-type material, where they can once again recombine with the valence band hole they have left behind, in the way sunlight creates an electric current. So, this is the whole cycle in which the electron holes and the electrons are generated, and they are trapped and they are photoexcited through the solar energy. P to N junction photovoltaic device. The whole process is that from the p type it gets excited, goes to the n type, and then in the conduction band joins the conduction band of the n type, and then finally through the outer circuit it moves out, and because there are holes created in the p type, they are then the electrons will flow out of the p type side into the n type, lose energy while moving through the external circuit, and then flow back to the p type, and thereby generating electrical current. Similarly, when we use this as a normal solar cell, but if we use dye sensitized solar cells, that is DSSC, where what is the role of the dye? Because the dye sensitized solar cell provides technically and economically incredible alternative concept to present day a P to N junction photovoltaic device. So, dye sensitized are one step further in trapping the solar energy. Dye sensitized cell, it is like that from p type semiconductor the electron move to n type, and that is what is causing the photovoltaic device to form. In contrast to the conventional system where the semiconductor assume both the task of light absorption and charge carrier transport, the two functions are separated here. Light is absorbed by a sensitizer which is anchored to the surface of a wide band semiconductor. Charge separation takes place at the interface via photo-induced electron injection from the die into the conduction band of the solid. So, it is slightly different as compared to taking two semiconductors of the p type and the n type. Here the light is absorbed by this die, which is a sensitizer, and then this sensitizer is actually anchored on to the wide surface of the semiconductor. Why is it called dye sensitized cell? There are then excites the semiconductor charge separation takes place at the interface via photo-induced electron injection from the die. From the die it goes into the semiconductor which is joining it, and then the whole process takes place. So, the rest of the part of the semiconductor pushing the electron to the conduction band remains the same. So, here what is happening? It is the die which is actually trapping the energy, and the excitation begins there, and then the rest of the functionalities remain the same as solar cells, and this become photovoltaic cell. It is only the role of the die that it traps sunlight and acts as a sensitizer. So, the name dye sensitized solar cell. Carriers are transported in the conduction band of the semiconductor to the charge collector. The use of sensitizer having a broad absorption band in conjunction with oxides of nanocrystalline morphology permit to harvest a large fraction of light. So, what it means that this dye is acting as a sensitizer, and then the broad spectrum band of the conjunction with oxides of nanocrystalline salts of titanium dioxide and other such compound can act and harvest a large fraction of light. Importance of titanium dioxide. The importance of this carrier, that they are transporting electrons to the conduction band from one semiconductor to another, is acting just like a charge collector, and these sensitizers can absorb a lot of light, and through the help of microcrystalline film, preferably titanium dioxide or thin oxide kind of nanocrystalline material, it permits to absorb more and more light through the dye that is impregnated on the titanium dioxide material or tin oxide material. So, the dye is actually on the surface of titanium dioxide or tin oxide. The dye absorbs the solar light, and titanium dioxide or tin oxide nanocrystalline structures are basically acting as a carrier. Nearly quantitative conversion of the incident photon into electric current is achieved over a large spectrum range extending from UV to near IR region. So, the sunlight, which is nothing but a source of electromagnetic radiation, has various types of light rays, and these light rays are ranging, which can be trapped, and they are from UV to IR region, which are trapped through these dyes. Solar cells have good prospects. Overall standard, solar cells such as dye sensitized solar cell can handle current conversion efficiencies up to 10%. That much has been at least achieved. So far, you see, it is one has many such cells in alignment, then one can generate substantial amount of current which can be used for lighting lamps and for all other domestic as well as industrial processes. Although it is only doing 10% conversion, but what it means that this 10% is from just one cell. If there are many such cells in alignment, then the magnitude of the current is high. There are good prospects to produce these cells at low cost than conventional devices. Here we present the current state of the field, discuss new concepts of dye sensitized nanocrystalline solar cells, including heterojunction variants, and analyze the perspective for the future development of this technology. Already the technology is quite developed, but there is always a scope of finding different variables and different variants of material, many new dyes, and let them tell you that these dye sensitized solar cells can be from dyes both from synthetic and from natural. So, here after this long background about dye sensitized solar cells, first we discuss what is solar cell, then what is dye sensitized solar cell, how it works, how it functions, what is the role of the dye which acts as a sensitizer, what is the role of the thin nanocrystalline structure of titanium dioxide or tin oxide acting as a carrier. One comes to a conclusion that sensitizers could be synthetic or from natural origin. How to design a low cost cell? In order to have a low cost, because these materials are all very expensive, so is there a possibility to have low cost sensitized solar cell? Otherwise, why should one go for it if one has to make photovoltaic cell or solar cells by cheaper material? Only then it is feasible and it is practical. Then dye sensitized solar cells, nobody would offer dye solar cells, sensitized solar cells. So, in order for popularization of those dye sensitized solar cell, which is our main subject of today's lecture, we are focusing mainly on where natural dyes can play a role. These offer the perspective of very low cost fabrication and present attractive features that facilitate market entry. It will not be taken up commercially if it is not cost effective. It is now possible to depart completely from the classical solid state junction device by replacing the contacting phase to the semiconductor by an electrolyte liquid gel or solid, thereby forming a photoelectrochemical cell. So, the only difference here is that one, and that is the design of a material which is of low cost material, and then only the cost will come down. Unless until these dye sensitized solar cells are cheap, they make no sense of being fabricated and they cannot be popularized. Total efficiency of dye sensitized solar cells. The total efficiency of DSSC is dependent on the nature, optimization and compatibility of each one of the components of the solar cells, and more particularly the photoanode, which plays a vital role in the charge generation and transfer processes. To increase the power conversion efficiency of DSSC, a nanostructured porous titanium dioxide with a wide band gap and large exciton binding energy is typically used in constructing the photoanode. So, what it means that main part is the photoanode, and that photoanode is made up of nanostructured porous titanium dioxide, which has a wide band gap and large exciton binding energy. The large surface area of the nanostructured titanium dioxide ensures the adsorption of sufficiently large number of dye molecules for efficient harvesting of the radiant energy from the solar energy. The dye, typically with a wide and intense absorption spectrum, is adsorbed on the titanium dioxide via anchoring groups such as carboxylic, carbonyl and hydroxyl group located on the dye molecule. So, that chelation that we learned in the dyeing and mordanting processes is applicable here also. Titanium dioxide has to offer good chelation, or rather titanium should, and that chelation happens through carboxyl, carbonyl and hydroxyl groups located on the dye molecule. A strong adsorption of the dye onto the nanostructured titanium dioxide is required for the efficient electron injection into the conduction band of the titanium dioxide semiconductor. So, the carrier and the sensitizer need to be very closely bound with a strong adsorption of the dye onto this titanium dioxide. So, slowly we are now moving towards the natural dye sensitized solar cells. Just the way synthetic dyes can be used, similarly can we use natural dyes for a non-textile purpose for making dye sensitized solar cells using natural dyes. And so, natural dye sensitized solar cells are a type of solar cells that utilizes natural dyes extracted from various sources such as fruits, vegetable, flowers and other organic materials to absorb sunlight and generate electricity. These cells are a promising alternative to traditional silicon based solar cells because they can be fabricated using low cost material and environmentally friendly processes. Here is how a typical natural dye sensitized solar cell works. Dye sensitization. Natural dyes such as anthocyanin from berries or chlorophyll from spinach are extracted and used to sensitize a wide band gap semiconductor material, usually titanium dioxide, which serves as a photoanode. The dye molecule adsorbs onto the surface of the titanium dioxide, forming a monolayer that can be efficiently absorb photons from the sunlight. So, there is a very even adsorption of natural dye, particularly anthocyanin from berries or chlorophyll from spinach, onto the nanostructured crystalline structure of titanium dioxide, which acts as a photoanode. How does the NDSSC work? Electron injection. When a photon of sunlight strikes a dye molecule, it excites an electron within the dye molecule to higher energy state. This electron is then injected into the conduction band of the titanium dioxide semiconductor, leaving behind a positively charged dye molecule known as the oxidized dye. Electron transport. The injected electron moves through the titanium dioxide semiconductor material towards the conductive substrate, usually fluorine doped tin oxide FTO, generating an electric current in the external circuit. Redox shuttle. To complete the circuit, the oxidized dye molecule must be regenerated to their original state by accepting electrons from a redox shuttle solution, typically consisting of iodide, triiodide ions, that is I minus upon I3 minus, or other redox couple which are usually dissolved in an electrolyte solution. See, there is first the formation of the dye which is adsorbed on the titanium dioxide. Then when the light falls on the dye, it absorbs sunlight and it excites the electron from the dye molecule, and it is then injected into the conduction band of titanium dioxide semiconductor. But the dye then becomes oxidized. Then these electrons which have been injected in the titanium dioxide semiconductors are then moving towards the conductive substrate like fluorine doped tin oxide FTO, generating an electric current in the external circuit. But now the circuit has to get completed. So, in order to complete the circuit, the oxidized dye molecule must be regenerated to original state by accepting electron from some redox shuttle solution, and typically it is the I minus iodide and triiodide ion combination of electrolyte which is used, which acts as a redox shuttle solution. Counter electrode. As at the counter electrode, usually platinum coated FTO, the electron from the external circuit and the oxidized dye molecule from the TiO2 surface combine with the reducing agent from the redox shuttle to complete the circuit, forming reduced dye molecules once again. Electrolyte regeneration. The reduced redox shuttle is then regenerated back to its oxidized state by receiving electrons from the circuit, external circuit, and transferring them back to the photoanode, where the cycle repeats. So, everything is regenerated. It is electrons are trapped by dyes, dyes then transfer it to photoanode, photoanode then transfer it to tin FTO, then from there it goes to the external circuit, and then the external circuit needs to be kind of refurbished, and the iodide and the triiodide solutions then do the rest of the electrolyte regeneration. Advantages of using natural dye sensitized solar cells include their low cost, ease of fabrication, and potential for use in flexible and transparent application. However, they also have limitations such as low efficiency compared to the traditional silicon based solar cells, issues with stability and durability, and the need for further research to improve performance and reliability. Nevertheless, they represent an area of active research and development in the field of photovoltaics, particularly for applications where cost effectiveness and sustainability are critical factors. So, they do have a market. It is not that they do not have any benefit, it is just for the namesake that natural dyes have been used. Because if we want to keep sustainability in mind, we can't use synthetic dyes for these solar cells, and therefore, they do have cost effectiveness and sustainability, which are critical factors to be considered while talking about the natural dye sensitized solar cells. Now, when we compare the NDSSC versus DSSC, many researchers have shown and have been done in natural dye sensitized solar cells for enhancing the efficiency and stability of the cell. However, still the efficiency of the NDSSC is less as compared to the synthetic DSSC because of the following reasons that are discussed. First, The efficiency of DSSC is low as compared with silicon crystalline solar cell. It can be enhanced with proper selection material such as substrate, dye and electrolyte. Nowadays, the application of graphene in DSSC enhances the efficiency of the cell. Secondly, degradation of dye in the presence of sunlight radiation causes stability problem in the DSSC. This problem can be resolved by proper selection of sensitizers that show stability at variable temperature. So, if we choose an ideal dye which will not get degraded in sunlight, then that is the most ideal solution. The synthetic dyes, that is the ruthenium complexes, show greater stability than natural dyes because of less degradation in sunlight in the presence of sunlight. Mixed dyes may show greater efficiency of the cell. Now, if you recall, natural dyes did have a fading effect in the UV light, and here is a bright sunlight which is full of UV light as well as IR light and all other electromagnetic radiations. Therefore, the sensitivity of the natural dyes is definitely more towards the degradation as compared to synthetic dyes. The use of liquid electrolyte results in temperature stability problem. The electrolyte freezes at low temperature and expands at high temperature, which can cause serious damage to the cell. Therefore, solid electrolyte based DSSC are in research nowadays. However, results low efficiency of the cell. So, if we change from liquid electrolyte, which is temperature sensitive, to solid electrolyte, the efficiency goes down, but yet there is lot of research happening in that area. However, coming back, even though natural dyes are not as powerful sensitizers as the synthetic dyes, the option for stability and sustainability and the environment friendliness overpowers every other factor. Dye sensitized solar cells convert visible light into electricity using sensitization of the cell. Performance of dye sensitized solar cells are mainly based on dye used as sensitizer. Nowadays, study of dyes extracted from natural resources is the main concern for researchers. Application of natural dyes is promising development in the field of this technology. So, here is another field where non-textile use of natural dyes is exemplified. Natural dyes are cutting down high cost of metal complex sensitizers and also replacing expensive chemical synthesis process through which simple extraction, whereas in natural dyes only simple extraction process can help. Natural dyes are abundant, easily extractable, safe material causing no environmental threat. These can be extracted from flower petals, leaves, roots, barks, fruits, from all sorts of sources of anthocyanin, carotenoid, flavonoid and chlorophyll pigments. This particular lecture where we are discussing natural dyes discusses development of natural dyes and their effect on various performance parameters of dye sensitized solar cells. Pomegranate dye as a source of natural dye. The performance of various natural dye containing pigments such as anthocyanin, xanthine, chlorophyll, carotenoid and flavonoid have been thoroughly investigated. These pigments are derived from various plant parts such as flower, petal, leaves, roots, fruit, pulp and bark. In a study, juice extracted from pomegranate was investigated as potential sensitizer for DSSC in comparison to other natural dyes. Directly the fruit juice was taken because it has a deep color. The pomegranate is a rich source of anthocyanin and we have deployed it as a sensitizer for the absorption of photons from the solar energy in DSSCs in generation of electricity. Anthocyanins are polyphenolic ring based flavonoids widely known for their antioxidant properties. They differ from other flavonoids by the presence of positive charge in the central ring and are responsible for intense colors of their fruits and vegetables such as berries and red cabbages. They have been shown to display a wide absorption emission band in the UV visible region of the spectrum as a result of electron charge transfer transitions. So, they are very receptive in actually taking the sunlight, and because they are very receptive in taking the sunlight, that results in strong electron charge transfer because they can take the visible and the UV light region of the electromagnetic radiations which are present in the sunlight. Natural dye sensitized solar cells. The dye sensitized solar cells provides credible alternative concept for inorganic solid state photovoltaic devices which are made from silicon. The conversion efficiency of DSSC is mainly based on the dye coated on the porous semiconductor titanium dioxide film, and this we have learned time and again. The use of natural dye in solar cells is a promising development to this technology because it cuts down the high cost of noble metals and chemical synthesis. So, if synthetic dyes are used, then they have to be chemically synthesized, and that is very cost intensive. Therefore, this type of solar cell has attracted considerable attention from the academic and industrial communities. People who are working in this area are looking at natural dye sensitized solar cells now more seriously. Numerous kinds of pigments such as anthocyanin, carotenoids, chlorophyll, flavonoids extracted from various plant components such as leaves, fruits and flowers have been tested as sensitizers. The photostability of the dye sensitized solar cell sensitizer material must be capable of undergoing many redox cycles without decomposition. That is a mandatory fact. If the dye sensitized surface cannot go through several redox cycles before it gets degraded, then it is of no consequence, and must also have the ability to carry attachment groups such as phosphonate or carboxylate to promptly graft it to the titanium dioxide. The development of natural dye photosensitizer and the mechanism affecting the dye stability is what is now the current research topic. The dyes extracted from pomegranate, berry fruits was successfully used in the fabrication of natural dye sensitized solar cells, that is NDSSC. The morphology, porosity, surface roughness, thickness, absorption and emission characteristic of pomegranate dye sensitized photoanode was studied. Pomegranate dye extract has been shown to contain anthocyanin, which is an excellent light harvesting pigment needed for the generation of charge carrier for the production of electricity. So, to our great surprise and advantage, one such natural dye extract was found to be excellent in its functionality, and it is excellent in light harvesting. This pigment is very good in absorbing the sun rays. The solar cell's photovoltaic performance in terms of efficiency, voltage and current was tested with a standard illumination of air mass 1.5 global AM 1.5 G, having a radiance of 100 meters watt over centimeter square. After optimization of the photoanode and counter electrode, the photoelectric conversion eta was 2%. The relatively enhanced efficiency is attributed in part to the use of a highly concentrated pomegranate dye, graphite counter electrode and titanium tetrachloride treatment to the anode, photoanode. And this is how the natural dye sensitized solar cell looks like. I mean, this is a pictorial description, it is not the actual description. So, there is glass top, there is positive electrode, there is FTO, that is graphite, and then there is electron current ion which is causing by the hole, the dye which is the sensitizing part, then you have titanium dioxide and the negative electrode and the electrolyte which is sitting there and the photons which are moving around. So, it is a pictorial description of how the dye which is just sitting small in one place on the surface of the titanium, microcrystalline titanium dioxide is playing a crucial role in absorbing the solar cell. When we look at these graphs, we understand that if it is only titanium dioxide, if it is only pomegranate dye, what is the absorption of the light, and when it is pomegranate plus titanium, a large amount of light is absorbed, and that is what is shown, that these are very good in terms of their utility. On the right hand side, the titanium pomegranate dye shows that in the region of 420 to 460 there is an intense peak which is due to the pomegranate dye, because titanium is white and pomegranate is absorbing a lot of dye. So, that means when you look at the photoanode and take an absorption spectrum of that, then this is the kind of spectrum that is achieved. The optical properties of pomegranate has to be very good in order to be a good absorbent. The overall performance of a DSSC is reliant on the light absorption capability of the dye sensitizer and the diffusion of the ejected electron through the mesoporous titanium dioxide film. The optical property of dye extracted from pomegranate were investigated using UV-Vis spectrometry. The absorption spectra of pomegranate dye extract bear TiO2 and pomegranate dye and TiO2 was just shown to you. The pomegranate dye extract exhibited an intense absorption broadband in the visible region at a peak of 510 nanometer. This intense absorption in the visible region, that is 510 nanometer, matches with that reported for anthocyanin and is the reason for efficient harvesting of the photons in the natural dye sensitized solar cells. So, if the dye has an intense absorption band, it is a good candidate to be used as sensitizer. That is the bottom line. Plant parts containing anthocyanin have been widely investigated for use as photosensitizers in the fabrication of natural dye sensitized solar cells. In addition to their high absorption coefficient in the visible region of the electromagnetic spectrum, the presence of hydroxyl and carbonyl anchoring group on anthocyanin enable their adsorption onto the surface. Now, what makes the dye adhere to titanium dioxide? The OH, if you remember the structure of anthocyanin, you will remember that there are OH and carbonyls, and these are the ones which help to adhere to titanium dioxide. This adsorption facilitates the transfer of the injected electron from the dye to the conduction band of titanium dioxide, which ultimately enhances the efficiency of natural dye sensitized solar cells. Excellent photovoltaic performance of the solar cell. Dye extracted from pomegranate fruit was utilized as the light harvesting analog. Dye extracted from the pomegranate fruit was utilized as a light harvesting analog in the fabrication of low cost, eco-friendly dye sensitized solar cell. The chemical, structural, morphology and optical properties of the pomegranate TiO2 coated FTO glass were investigated. The excellent photovoltaic performance of the solar cell could be attributed to high concentration of anthocyanins present in the pomegranate dye utilized in the sensitization of the nanocrystalline titanium dioxide. The use of graphite as a counter electrode and TiCl4 treatment of the photoanode improved the solar cell efficiency by more than 1%. So, from 2% it became 1% extra. So, total now it became 3%. Now, working principle of the DSSC with delphinidine dye. This is a natural dye. How delphinidine absorbs the light from the solar energy, how it transfers to the titanium conduction band, and then from titanium it again goes to the external circuit to the cathode because this is a photoanode which is made from the titanium dioxide. And this is how the circuit gets completed, and the electrolyte, that is iodide is to triiodide system, gives the electron back to the oxidized dye. So, this is what is a pictorial description of the working principle of DSSC with delphinidine. We can call it NDSSC. When you look at a comparative data as to which one is better from the cost of from several factors, whether synthetic dye is better than natural dye, because everywhere we are trying to compare and we are trying to show the supremacy of natural dye. So, if we take the parameter cost, complex material formed by different chemical reaction therefore results in high cost. So, synthetic dyes are costly, low, and whereas natural dye, locally available resource extracted from plants, flowers, fruits and roots, this results in low cost. Second factor is environmental effects. So, synthetic dyes have bad effect on the environment due to its chemical nature. They are non-biodegradable, they are toxic, etc. Whereas natural dyes, less effect can be seen on the environment due to being its natural occurrence. Third factor, stability. Synthetic dyes slowly degrade in the presence of sunlight, therefore, long life of DSSC is at stake, and therefore, it provides long life. whereas natural dyes degrade faster in the presence of sunlight, results in stability problem in DSSC. Fourth point, absorption on solar spectrum. The N3 dye has absorption up to 800 nanometer, whereas in natural dyes the dyes have shown absorption in broad range of visible region, that is 400 to 700 nanometer of the solar spectrum. Efficiency point of view, DSSC based on synthetic dyes have shown higher efficiency as compared to NDSSC. The efficiency of NDSSC is certainly lower due to degradation of natural dye. Availability, noble material, thus no long term availability, and synthesis of these dyes, the use of petrochemical which is slowly depleting, is now quite an alarming issue, whereas natural dyes are 100% available all the time. Fabrication process, synthetic dyes require multi procedures which involve a variety of solvents and time, and also purification of the contaminants, whereas natural dyes are simple and direct chemical procedures. Only they have to be extracted and used directly, no need even to purify, only the extraction and efficient extraction can work. Even cocktail dye sensitizers have been used. What does the word cocktail means? A mixture of more than one or two dyes. Various natural dyes can be combined in appropriate portion to form cocktail dye sensitizers. This might be an alternative to increase the band absorption and as a result to improve efficiency of the dye sensitized solar cells. Thus, economically viable option is cocktail natural dye. A cocktail dye mixing chlorophyll dye and anthocyanin dye in 5 different volume ratios have shown conversion efficiencies going up by 1.95%. The mixing of different pigments present in the natural dyes can also give better results. The sensitizer is the heart of the dye solar cell and should not degrade fast, which leads in increasing the life of the cell. It should have high extinction coefficient. There should be good electronic binding between the sensitizer and the semiconductor. Hence, the dye should have a carboxylic group and the hydroxyl group, and that we have plenty in natural dyes. Hence, mass production of DSSC can be done. Mass production of DSSC can be done by ensuring all the above properties of sensitizer. Natural and synthetic sensitizers are required to enhance the absorbance of solar radiation from visible to near infrared region of the solar spectrum. Therefore, more solar radiation is able to penetrate into the dye, that increases flow of electron in the semiconductor. So, by taking a choice of 2 different dyes, that is a chlorophyll dye and an anthocyanin dye, the dye absorption, the photon absorption could be enhanced, and therefore, these sensitizers are able to trap the solar radiation from visible to near infrared region. Why natural dyes? Because they are available. Fruits, flowers, leaf, bacteria, etc. exhibit various colors and contain several pigments that can be easily extracted and employed in DSSC. Advantages of employing these natural dyes as photosensitizers in DSSC are due to their large absorption coefficient in visible region, relative abundance, ease of preparation and environmental friendliness. Most importantly, the synthesis route of natural dye based DSSC is cost effective and it does not involve noble metals like ruthenium dyes. These plant pigments exhibit electronic structure that interact with sunlight and alter the wavelength that are either transmitted or reflected by the plant tissue. This process leads to the occurrence of plant pigmentation and each pigment is described from the wavelength of maximum absorption, that is the lambda max, and the color perceived by humans. Pigments from natural dyes include chlorophyll, carotenoid, flavonoid and anthocyanin that are relatively easy to extract from natural products when compared to synthetic dyes. The efficiency of NDSS has been shown to be based on the fact that how good the dye molecule is, how well it is adsorbed on titanium dioxide surface and also with the maximum absorption coefficient of the dye. Improved charge transfer leading to higher efficiencies can be accomplished and with enhanced interaction between the titanium dioxide and the dye molecules. The acid pretreatment of the titanium dioxide film can cause the shift in the conduction band of the titanium dioxide. Often crude and fresh extracts of natural products yielded good efficiency than commercial or purified sensitizers. This could be due to the presence of ancillary molecules like alcohol, organic acids, etc. that suppresses the recombination of electron with electrolyte favoring charge injection. Anthocyanin of course then is the main choice of dye, and this we have seen that anthocyanin has been proven from the pomegranate juice to be one of the best available natural dye source. Investigations on other types of plant pigments like flavonoids and carotenoids are relatively lesser when compared to anthocyanin. Therefore, they are very good as photosensitizers which trap the solar energy. Optical images of the extracted dye from onion peel, spinach and cabbage has been shown here, and they are very easy to extract from these sources. The extraction is even simpler as compared, because even the dilute solution can work as natural dye for the solar system, for the solar cell system. Different types of natural dyes have been used. People have attempted to use many other dyes, and there is a huge range of dyes that have been already explored for NDSSC. Chlorophyll is a good sensitizer, and that we have understood because when cocktail dye was used, it gave better result even when simple anthocyanin was used alone. So, chlorophyll and anthocyanin gave better results. So, chlorophyll definitely is a good photoreceptor. Hence, chlorophyll absorbs light in a wide wavelength range corresponding to blue, red, violet region of the visible spectrum. It demonstrates efficient anchoring to the titanium dioxide surface, that is the photoelectrode or the photoanode, thus enabling an effective electron injection mechanism in the NDSC. So, with this we have come to an end of this chapter, where we were discussing an alternative use of natural dye, and this is a completely different use. Initially we were only talking about natural dyes in the use of textile, but we saw how natural dyes can also be used as acid base indicators, and now these natural dyes have been used in dye sensitized solar cell fabrication. So, with this we have come to an end of this lecture. Thank you.